the equations of lines and planes. So lines are relatively more straightforward, but planes indeed will require the knowledge of the plots. So let's quickly give you guys the formulas that are needed for this section. So lines, there are a few equations. Okay. So the first one is R equal to R0 plus TB, which we'll explain a little later in more detail. But here, basically, this is in the vector form where R0 is a point on the line, V is the direction along the line, and R is a vector representation of whatever point on the line. You can also write it as another form where R is represented as x, y, z. So this is just saying, okay, the x component is x0 plus TA, y component is y0 plus TB, and z component is z0 plus TC, where ABC is a vector that's just the vector v, okay, along the direction of the line. And also here you can see there's a t, which is a parameter. Right? If you try to eliminate that the parameter and only keep x, y, z in the equation, then you will get with something like x minus x0 over a equals to y minus y0 over b, and that equals to z minus z0 over c. So this is another equation that can represent the line. In the case that A, B, C are all non-zero. So this is so now these are the three important equations for lines. And that's pretty much everything that you need to know about lines. And then for the planes. So we begin with the vector form first. So this is a vector n, which we will know later as the normal vector of the plane. That dot with a vector within the plane to be a 0 on the right hand side. Okay. So just saying we will have a vector little n that's actually perpendicular to whatever vector within this plane. Okay. Once again, R is just the vector with components x, y, z, and R0 is whatever point within the plane. And also we can write it as another way. So let's say x plus by plus cb equals some constant. Or we can write it as a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. And now the third equation is actually what's called the scalar equation, which is just writing the first equation in another way, okay, in terms of x, y, z. Okay, so now let's elaborate a little bit more. Let's firstly start with the lines. Given a point T0 with components x0, y0, z0, hence the corresponding vector R0. So R0 just represents a vector that has a head on the line. Okay. So that's exactly OP0, which is the vector x0 to z0. We have a point P0 on the line, and we call that line capital L. And a vector V parallel to the line capital L, then the vector equation of L is R equals to R0 plus TV. Okay. So this is actually pretty straightforward. So from the point P0, you can extend along the line as long as you are just following the direction V. Okay, so because V is a direction that's parallel to this line. So to give a figure, it's actually in 3D. Let's just quickly sketch. So we have the coordinate system, and let's say we have a line, okay, in purple. So P0 is whatever point that you pick on this line, and then this vector R0 is what? R0 is actually this one, just going with the head at P0 and the tail at the origin. Okay, so this is the vector R0 that we start with, right? And then what is vector V? V is just the direction that's parallel to the purple line. Okay, so it's vector like this. Okay. So in fact, for V, the magnitude doesn't matter that much as long as it's non-zero and along the direction of the purple line, it's going to be good, right? And then if you think about expressing whatever point on the line, like right here, then you see, let's say this is P. Okay, so let's say this point P is whatever point on the line. Then you know, okay, the vector P0P is a scalar multiplication of vector V. Okay, so you see this one is TV for some scalar T. Okay, so you know, and this vector here is R0 plus TV. Okay. So just the sum rule. Okay, well, the triangle rule. And now, so this is the case where T is a positive scalar, right? What I meant is if it's negative. So on the other side of the black point, it's also really similar because it just make the vector TV to have the opposite direction. So like if you have a point like this, okay. So in this case, you just flip the sign, right? So it's going to be TV, but T is negative. That's right here. Okay. And then this vector is still the triangle law. So R0 plus. Pretty straightforward, right? So now you see, okay, as long as you have a point and the direction, you can define the line. So it's good. Okay, so now let's put down the components. If V equals to the vector ABC, R0 is a point that has X0, Y0, Z0 as the components. And finally, if we represent R as the unknowns, X, Y, Z, then we have, so just rewrite the top equation. Okay. The top equation is in the vector form. We just rewrite. So X, Y, Z is replacing the vector R. X0, Y0, Z0 is replacing R0. Now t is just a scalar, which is a parameter, but then v is now ABC. It's a vector of three constant components. Okay. And if you put the components all together, then this one is saying this is exactly TA, TB, TC as the three components, right? And you can do the addition to x0, y0, z0. So eventually this is x0 plus TA, y0 plus TB, z0 plus TC. So you can express it in another way. And that will give us the second equation, which is called the parametric equation of the line. So this is saying, okay, x must be x0 plus TA, right? Plus, yeah. And at the same time, y must be y0 plus TB. Finally, z must be z0 plus TC. So this is the parametric equation of the line. Okay. And here, E is a parameter. And here t can be whatever real number that you want. Now, finally, like we mentioned, as long as we have the parametric equation, we can derive that third equation where we eliminate t, right? So as long as a, b, and c are non-zero, then we can just subtract both sides, just get rid of the constants all to the left-hand side. And then we can divide a, b, c within these three equations respectively. So that will eliminate t. Okay. Then eliminating t above, we have what's called the symmetric equation. X minus x0 over A equals to y minus y0 over B equals to z minus z0 over C. Okay. So essentially they're all equal to t, but then we don't really want t anymore, so we throw that away. So that's this relationship. And this is called the symmetric equation. And you see the symmetry, right? Because essentially these three expressions are of the same form. So it's going to be x minus x minus the x component of the point of whatever point on the line. You divide by the direction of v on the first component, and then you do the same for the second. You do the same for the third. And then they all have to they all have to equal. Yeah. Remark. So now we are saying A, B, and C they need to be all non-zero in order to get this symmetric equation. So if we have A equal to 0 and B, C are non-zero, then we cannot really divide by A. So that's something unfortunate. But we can still write the symmetric equation. So here the idea is the following. So we see when A is 0, then this thing is t times 0, then it's always 0. Okay, so that tells you you cannot really divide by 0. But then you can just write x equal to x0. So that's and you just make the equality for the from the other two. So here x equals x0. That's something you cannot really do as the equality like right here. Okay, so this equality will not be expressible, but the rest is gonna still follow. So now the symmetric equation just have a different form. So V describes the direction of the line L, R0 describes a point on the line L. Example, describe line L through the following 2 points. A with components 2, 4, -3, and B with components 3, -1. Okay. So here we just need to realize that we only need 2 things. One is 1 point on the line, and the other is the direction along the line, right? So R0 we can just pick. So A and B. So whatever you choose. So if you choose A, then this is going to be OA, which is the vector form of the point A. And of course, you can choose OB, right? But that's something you can try on your own and see if you get something different or you get something the same. Okay? So basically the idea here is that regardless of the point that you choose on the line, so the line equation will still represent the same thing, right? So that's something try to do yourself and see if that's the case. And now the direction along the line, right? So if you go back to the figure, so if we go back to the figure right here, so this vector along the line is this one. So basically, whatever 2 points that you pick along the line, and you, so whatever 2 points that you pick, this direction is going to be parallel to B, right? So here you can just choose A and B and do the difference. That will give you a vector along the direction of the line, right? So V can be AB or BA, doesn't matter that much. But then here, this is the head minus the tail. So the component of B minus A, so it's going to be 3 minus 2 for the first component, -1 minus 4 for the second component, 1 minus -3 on the third component. So now this is 1 -5 4. Here, I would also like to mention that you can choose, of course, a different V. Okay, so you can choose V equals to BA. You can choose V equals to, let's say, 1/2 of AB, right? So I'll try and see if it gives you something different. So here now, the vector of the line is going to be R equals to R0 plus TB. So we can write it as what? So now we do have what is R0 and what is V, right? So we just write it down. So it's going to be 2, 4, -3. That's for R0 plus T. Now we have V as 1, -5, 4. So let's say if you just have a scale, if you just divide by 2 for this part, like right here, then this is the component wise different. division in front of t. So essentially that's not different at all. Okay. Now the parametric equation. So basically for the parametric equation, we just need to express everything in terms of x, y, z. Okay. So just saying that the x component has to be 2 plus t. The y component has to be 4 minus 5t. And the component has to be -3 plus 4t. And finally, we have the symmetric equation. And for symmetric equation, what do? We just eliminate the variable t, right? So it's going to be 2x minus 2 over 1. That equals t from the first equation above, right? And then y is going to be y minus 4 over -5. And for z is going to be z minus -3, which is z power 3 over 4. So basically here, what do we have? We have this symmetric equation of the line. And here we want to talk about the intersection between the line and a axis plane. Okay, so xy plane, that's it. So basically, if you want to find out the intersection between this line and the coordinate plane, xy plane, what do? So you just need to realize that the point on the xy plane that has the coordinate to be a 0. So this remark is the remark that I added at the end of last class. So this essential idea is that for, let's say, the coordinate space. So we are looking at the intersection between line and the bottom plane. That's the xy plane, right? So let's say the line is something like this. Okay. And then essentially we're looking for this this black dot. Okay, so that's the intersection. And in this intersection, the z value is 0. Okay. So now what do? So this is really similar to what you have seen in the xy plane, where if you have a line like this, right? So this is a two-dimensional thing. So the line can intersect the x-axis for one point at one point. It can intersect the y-axis at one point, right? So when you get the x-intercept right here, what you need to do, intercept. What you need to do is you use the line equation and say y equal to x plus b, and you just make y value to be 0, and then solve for x, right? That's the x-intercept. And then for the y-intercept, what do? You just make x value equal to 0 and you solve for y. Right? So here is going to be the substitution of z equal to 0, okay? Because we want the point it's on the xy plane so that the z coordinate is 0. So I can actually cheat a little bit by just copying this part. I only want to make sure that the z value is 0. So here I just want to replace this z by 0. And we do realize that here we actually have two different equations. Okay? So the most right-hand side actually is a constant, 3/4, right? But then we notice that this 3/4 is equal to x minus 2. So the most left-hand side is x minus 2 over 1. That equals to the 3/4 right here. This is 0 here to just indicate that we have three parts of the equation, right? So the middle part also have to equal to this 0 plus 3 over 4. Okay. So now, from the equation at the top, you will see, okay, x must be 2 plus 3/4. And from the second equation, you realize, okay, you have to multiply both sides by -5. That's going to be y equals to 4 minus 15 over 4. Okay, so eventually, we can solve and have x equal to 11 over 4, and y has to be 1/4. Okay, so now this tells you what? This tells you the points of intersection with the xy plane is having the coordinates 11 over 4, 1/4, and 0. Okay. So the intersection is exactly this point. 11 over 4, 1/4, 0. Okay. Any questions so far? Next example. Now, in this situation, we have two lines. We have one, L1, with the parameter t. So it's going to be x equals to 1 plus t, y equals to -2 plus 3t, and z equals to 4 minus t. And now we have another line. So when you have another line, then the parameter should be another parameter. Okay. So L2 is going to be x equal to 2s, y equals to 3 plus s, and finally z is -3 plus 4s. Okay. So we need to realize that we somehow need to use separate letters for the parameters, because if you just use t all the time, then those t's are not going to have the same value. Okay. Because they should mean a different thing when you are varying along a line. Okay, they should be independent of each other. Okay, all right. Now here comes the question: do they intersect? And also, are they parallel? So if L1 and L2 intersect at some points, we don't know what the point is, so we make the coordinates unknown to be x, y, z. Then basically that tells you what? It tells you x, y, z will have to satisfy the equation of L1 and the equation of L2, okay, the parametric equations. Then the point should satisfy both parametric equations. That is, so basically x, so these two x values must equal, y values must equal, and z value must equal. Okay. If you look at these three equations, actually the most right-hand side and the middle part will matter. So if you can find the t and s that satisfy all the three equations, then you will find the intersection. Or If you cannot find the pair of T and S that satisfy these three equations, then you cannot find the point X, Y, Z that's the intersection of it. So we have equation system solves. That's three equations. So now three equations and three equations and two variables. Okay. So usually you can solve T and S from let's say 1 and 2. And then if 3 is satisfied, then great. All the three equations are satisfied. If 3 is not satisfied, then okay, there's no such an intersection. Okay. So solving let's say 1 plus equal to 2s. So here we can think about is you can do the rule of elimination, or you can do the rule of substitution. So here, let's say you want to substitute by using the second equation because you see so on the right hand side you have s plus 3, right? So you can minus both sides by 3, and you can say here I'm going to put it in red. So s is 3t minus 5. And then you can substitute in the first equation, that's going to be purely independent t, right? So in the end, you will be able to solve the t from equation 1. So the method is not so critical that you may probably have seen before. But then once you solve a t, and then you can just plug back into the this event equation. Or you can just plug back into equation 1 and just divide both sides by 2. That will give you s. So s is going to be 8 minus 8 over 5. Okay. So this is just some algebra. But then now we just want to verify that equation 3 is satisfied or not. Okay. Substituting. Equation 3, we have something interesting. So if you look at so we have left hand side, we want to match with the right hand side. Okay. But now let's say 4 minus t is left hand side, which is 4 minus 11 over 5, right? So 4 is actually 20 over 5. So you do the difference, that's actually 9 over 5. Now the right hand side is what is negative 3 plus 4s. So 4s is 32 over 5, and then you minus 3. That's 17 over 5. So the left hand side does not equal to the right hand side of equation 3. Okay. So this tells you what? This tells you although you can find a pair of s and t that satisfy equations 1 and 2 at the same time, let's just say okay, the xy coordinates you can make them to equal, okay, for these two lines. But then at the same location of x and y, the z values are different. Okay. So essentially, you cannot really find the intersection of these two lines. So if you try to make x, y, z values all equal, then you can only satisfy two equations. So that's what happens here. So our system of equations 1, 2, and 3 has no solution. hence L1 and L2 do not. That's good. Any questions so far? Okay, so now let's whether they intersect or not, right? And now we have the other part of the question. We want to determine whether L1 and L2 are parallel or not. Okay. So now we can utilize the parametric equation to get the direction of the line, right? From the parametric equation, we can obtain vectors along the directions of L1 and L2. So basically, we just want to write the parametric equations in terms of the vector form, okay? In terms of vector equations. For instance, if you look at L1, so if you go look ahead, this is x equal to 1 plus t, y equals to -2 plus 3t, z equals to st. So we're writing it again because we want to somehow convert it to the vector form where my vector r is representing the x, y, z as a coordinated vector, but then we can write it as 1, -2, 4 with angle brackets plus t times the vector in terms of 1, 3, negative. Okay, so basically taking the coefficients in front of t, that will give you that direction along this line. So this part, this is the vector b that we have for the vector equation of the line. Right? This is describing the direction of the line L1, right? And then you can do the similar thing for the parameter s with respect to L2. So here we can conclude that 1, 3, -1 is along the direction of L1. Similarly, looking at coefficients of parameter s. So, well, this step, you don't necessarily need to write it out explicitly, but so I'm just enclosing it in parameters. Basically, we are looking at coefficients in front of s. That's going to be 2, 1, 4. Okay, so this is actually a pretty different direction from the direction along L1. Okay, so 2, 1, 4 is along the direction of L2. So basically, if one of the vectors right here is scalar multiplication of the other, then they are along the same direction. Okay, so opposite. If the scalar multiplier is a negative number, but here we see this one has all positive entries. So if you do a scalar multiplication, they all stay with the positive sign, or if you multiply by a negative number, they will always stay a negative sign, right? For every entry. But here there's a mixture, so they cannot be a constant multiplier of another. Okay? So this is something quite straightforward, isn't it? So we put it down in words, however. These two vectors, 1, 3, -1, and 2, 1, 4, are not scalar multiplication of each other. So we notice that they are not parallel. So if you think about it, within a single plane, the two lines are either parallel or they intersect, right? But now in three-dimensional space, it's possible that we see some two lines like this, L1 and L2. They do not intersect and they are not parallel. So remark. When that happens, the two lines are called the skewed lines. If they do not intersect, no parallel to each other. Okay, so in this situation, it's kind of intuitive to visualize that, say this L1 is probably some line like this, but it's a bit higher than another line that's L2. This, so basically, in the spatial kind of vision, so they don't really intersect. Because here, in this figure, if you imagine in 3D, L1 is a little bit higher than L2, but they certainly they're traveling along different directions. Okay? So essentially, you are able to construct a plane that's containing L1, and you can construct another plane that's parallel, but containing L2. So these two are parallel, but they're just not intersecting at all. Okay, so these two planes. Okay, let me try to do this a little better. So these two actually, well, especially speaking, one of them is the left one is higher, the one on the right is lower, but they just never intersect. Okay. So now each plane contains a line. So eventually these two lines never intersect. Right. Now we mentioned this concept of the plane, right? So what's important here? So let's talk about the planes. Basically, if you recall, we mentioned that at the beginning of the section, we only need two things. We need a point on the plane, and we need a direction n, which is later called the normal vector. Okay, so given a point d0, let's say the coordinate is also x0, y0, z0, and a vector, let's call it little n. We may define a plane. We may define a plane in 3D that is perpendicular to this vector n. So basically, actually for a plane like this, okay, so that's just a quick sketch. So you can think about a direction that's exactly perpendicular to the entire plane. Okay? So that is the normal vector equal n that we are looking at right here. And that being said, basically, this solid point is the point P0 that we start with. And then if you think about this normal vector n as the vector that's perpendicular to the entire plane, then for whatever vector that you draw with the head on the plane and the tail being P0, for whatever P that is, it's always perpendicular to this normal vector. Okay? So whatever that point that you pick, this is not so easy to indicate that they are perpendicular. Think about this direction P, right? That's still perpendicular. If you choose that kind of direction, it's still perpendicular. So then the idea here is that for whatever vector that you have, let's say this is the pen that have this direction n, right? And then so the idea here is that this vector there should exist a plane that's perpendicular to it. Basically, that's the one that's perpendicular to this direction. Okay? And you choose a point along the line that will give you that P0, and so eventually you will be able to define that equation that's going through the point and then perpendicular to the direction n right here. Okay. So now let's put the things down. So P0P and n are orthogonal. So they're always perpendicular to each other, no matter what what that point P is, right? So thus, to put them down, we can express it in the dot product. Okay, so P0P as a vector dotting with n is always 0. Okay, so when they're always orthogonal or perpendicular, they just dot and always get a 0. Okay. So now that tells you, therefore, for any point P, and let's say the coordinates are x, y, z on the plane, we can simply rewrite this dot product in terms of the coordinates, right? So P0P, so P is the head, P0 is the tail, so it's going to be x minus x0 at the first entry, y minus y0 at the second entry, z minus z0 at the third entry. That's my vector P0P, right? And now I'm just saying this vector dotting with n is always going to give you a 0. So that's looking really close to the formula that we had at the beginning of this section. So if you specify the coordinates of the small vector n, let's say to be ABC, then this equation is even more explicit. Okay? Then this equation becomes what? This equation becomes a times x minus x0. So the product of the first coordinates plus b times y minus y0 plus c times z minus z0 all equals 0. Right? So explicitly write out the dot. So that here, this is the vector equation. Okay, so this is now that we substitute. This is standard equation of the plane. And now if you combine these constants, okay, so you see you have negative ax0, negative by0, negative cz0. You can distribute and combine the constants. You can have something like ax plus by plus cz plus some constant d. Now that d is just the combined copy of all the constants, okay, where d is negative x0, negative y0, negative c0. Okay. So that's the equations of the plane that we started with this section. Okay. Remark. The vector equation of the plane is exactly well. So basically here we just rewrite this by replacing the coordinates of P0 and P. Okay. So we just need to say n starting with r minus r0 is always a 0. So that's exactly the vector equation. So everything now is in the terms of vector. Okay. Where we just recall that we always represent r to be the vector starting at the origin with a head at the point P, which has coordinates x, y, z. And r0 is just whatever point that you pick on the plane. So OP0, which is the point x0, y0, z0. So that's the vector equation that we started at the beginning. But then you can also now you can rewrite this equation just by putting the constants on the right hand side. Okay? So n starting with r0 is actually a constant. You can equivalently write n starting with r equals n starting with r0. So this is another form, but it may look interesting. Okay? So if you think about it, this is just saying, okay, whatever x, y, z vector, which is little r. Okay? So whatever vector there, so n starting with that vector equals to this fixed constant. Okay? So n starting with r0 is just definitely a constant when you have n and r0 sets specified, right? So that's actually also really similar to this. Okay? So ax plus by plus cz is actually this part. Okay? But then if you move the d to the right hand side, that's exactly the right hand side constant. Okay? So they're highly related. Okay, some more terms. Here, n is called the lower vector of the plane. The scalar equation of the plane is that's equation that's explicitly writing out the dot. So a times x minus x0 plus b times y minus y0 plus c times d minus d0. So this is the scalar equation. Sometimes they call it the standard equation. Okay. And they also have another name for the top equation that we see on this screen. So they call it the linear equation. Okay. So let me write it down. It's the linear equation of the plane is the one that you get when you combine all the constants. So x plus by plus c equals well, plus d. So this is called the linear equation. Right? And that's all the terminologies. Okay? Example. So let's say we have a point P0 and it has coordinates 2, 4, -1. And then let's say we have a little n, that's the lower vector with coordinates 2, 3, 4. Okay, so now let's write down the scalar equation and the linear equation. Okay, so the scalar and linear equations are the following. So thinking about the scalar equation, you just write down. So n has 2, 3, 4, right? So that's in place of ABC in the top equation, in the top scalar equation. So it's just going to be 2 times x minus x. Well, now x0 is a 2 from the x entry of P0. Right? So yeah, so why don't we put the constants of ABC first? So 2, 3, 4, right? And then for the differences, right, of coordinates, so that's just going to be x minus x0, which is x minus 2. Y minus y0, that's y0 is not 4. Z minus z0, so z0 is -1, so you minus -1, it's actually plus 1. Right? Sounds good. And then we combine the constants that will give us the linear equation. So it's going to be 2x plus 3y plus 4z if you just extract the xyz terms when you multiply things out, right? But then we still need to keep in mind about those constants. So it's minus 4, minus 12 plus 4, so it's minus 12. So the -4 and the +4 at the beginning and the end, they're cancelled. Okay, so that's relatively straightforward. But now let's think about. So this is a plane, right? So what about the x, y, z intercepts of this plane? So basically, the intersections of the plane with the coordinate axes. Okay, so the x, y, z intercepts. There are 3 intercepts, right? So when you think about the x-intercept, they're just saying, okay, along the x-axis, that means y, z coordinates are all zeros. Okay, so you can just make these zeros, and then okay, that tells you x must be what, 6. Okay. So the x-intercept is 6, 0, 0. I'm just gonna directly write it down. And then if you think about the y-intercept, let's just say, okay, my x and z has to be 0 because I'm lying on the y-axis. That tells me my y must be 4 because 3y minus 12 is 0, right? And finally, my z-intercept is that I have to make x, y to be 0 and lying on the axis. That tells me x, y are zeros and z has to be 3. Any questions so far? Yeah, okay. And so to illustrate in the axis, let me basically you have what? You have 6, 0, 0 along the x-axis, 4 units along the y-axis, and 3 along the z. So it's going to be like 3 here. That's along the z direction. X direction is longer, so that's a 6 here. X z. Let's say here is 4. Right. So basically, this plane, what? Just go through these intercepts, okay? So z intercept right here, x intercept right here, y intercept right here. So if you want to sketch the plane, it's gonna be, it's gonna go through the 3 quarters of a triangle, right? So it definitely will go through this triangle right here. So it definitely has to go through. So let me try again. Okay, this looks better. So now the plane will certainly contain this entire triangle, and just so possibly it will be something like this. So this is the plane that you have. Okay, this is going through the red triangle. Okay, going behind these axes. Right. Next example. Find the plane that passes through 3 points. P, Q, R. So P having coordinates 1, 3, 2. Q having the coordinates 3, -1, 6. And finally, R has the coordinates 5, 2, 0. Okay. So basically, 3 points within the three-dimensional space will define your plane as long as they are not along the same line. Okay. So then we want to find exactly what that plane is. Okay. Basically, the idea here is that you have a plane, right? You are looking for this plane, but you know there are 3 points. The location doesn't matter in this situation. So let's say it's Q, P, and R, right? So now you know the 3 points. Realize that for a plane, you only need 2 aspects. One is just any point on the plane, that'll be good. And the other aspect is that you need that null vector. You need the vector that's perpendicular due to the plane. So somehow we have 3 points. So we somehow want to what we can do is that just pick a vector and another one. So that's QR and QP, right? And now so the null vector must be perpendicular to both of these vectors. So you can just do the cross. Okay, so that will form you the null vector that's in this situation in the figure here is QP cross QR, right? But then actually, so there is a freedom of choice. So just letting you guys know. Give it a little more space. So, and of course, it can be something like PQ cross PR, right? Starting if you start from the point P, right? Or even just RP cross RQ. So these are 3 different ways that you can calculate, right? But then we just pick one. That'll be good. Okay. Make sure to if you have the time, make sure to double check, play it with yourself that whether indeed we're getting the same equation of the plane. Okay. So let us compute. So actually, any choice would be good as long as you're not just crossing the vector with itself. Okay. So let's just say PQ cross PR. So the point here is that just pick 2 edges of the triangle and then do the cross. That should be good. So now you can also just do the differences of vector of this vector components within this 3x3 determinant. So if you are doing PQ, so now essentially we're doing this choice. Okay? We're doing PQ cross PR. So it's just going to be the head minus the tail. So the common tail is P. So we have what? We have 3, -1, 6. Subtracting the coordinates of P. So it's 3, -1, 6 minus 1, 3, 2, right? And then we for the third row we just do the coordinates of R, which are 5, 2, 0. Subtract by the coordinates of P, 1, 3, 2. And then we just simplify the entries, and once we do that, we are able to just multiply things out by definition, right? So the middle row gives you 2, -4, 4. The last row gives you 4, -4, -2. Okay. And now everything is every entry is a constant number, so we are able to just what? So for I, we just eliminate first row, first column gives you a 2 by 2, and then you just keep on doing for j and k, right? Just be reminded that for the entry j, the constant there they need to be negated, right? So here, make sure to do yourself, double check with your work, then you should get 12i plus 20j plus 14k. Okay. And of course, once you get this result, you always try to verify whether this is the correct vector by doing this, starting with this row. So if you dot, you get what? You get 28 minus 20. Well, excuse me, 48 minus 20 minus 28. Okay, that's exactly as good. And I would expect that will be the same if you are dotting this vector with the second row. Right. So double checking, very important. Right. So now we get that vector n. Okay. So now we have n, and then you just pick whatever point that you need on the plane to get the equation of the okay. So choosing P, which is 1, 3, 2, as point P0 on the plane. And let me write in the red bracket again, so about the comments that Q and R can be chosen instead. But if you feel that you need to verify this, make sure to do that. Okay. Then we have the following equation. So the components of n just go at the front as ABCs, right? And then we just put in the x0, y0, z0 coordinates in the equation. It's going to be 12 times x minus 1 plus now 20 is b, right? Y minus the y entry of this point is 3. Finally, 14. Z minus z0 is now the z entry of the point P is 2. And then we're done. Sounds good? Any questions? Right. So a few more examples to go. Example. So now let's say we have a line and a plane. Okay. Find the intersection of the line, which is having the parametric equation x equal to 2 plus 3t, y equal to -40, z equals to 5 plus t. And there's a plane and the plane. 4x plus 5y minus 2z minus 18 equals 0. So let's call the equation, the parametric equation of the line to be equation 1. And the plane equation is equation 2. So we just want to find the point x, y, z that satisfy both equation 1 and equation 2. Right? But now if you think about it, equation 1 is just saying every component, every entry can be represented as in terms of t, right? So what we do is we substitute equation 1 into equation 2, and we solve that value t. Okay. Substitute one into equation 2. So now we have what? We have 4 times, okay, x now is replaced by 2 plus 3t. Now y is replaced by negative 4t. Z is replaced by 5 plus t. That's 18 equals 0. Okay, if we do this substitution, we see, okay, indeed, we have one equation only in terms of t, right? And then we can just solve. Okay, so and actually there are a few possibilities when we get to this equation. So it's possible that okay, you can simplify and you can solve for one value of t, right? That means what? That means you have one intersection. Right? But then if this equation always holds, so everything cancels out, you have 0 equal to 0. That tells you, okay, this line actually there were infinitely many intersections. That means this line is within the plane. But then if this thing never holds true, let's say that's something like 3 equals 0, so it's never true. Then that tells you, so these two things will never intersect. Okay. That's but for this situation, we just simplify. What do we have? We have 12t minus 20t minus 2t. That's negative 10t. 8 minus 10 minus 18. So negative 20. And okay, we solve that, we will get what? We'll get t equals to negative 2. Okay. So now we have negative 2. So that tells you what? Okay, there's indeed one solution. So you can substitute back into equation 1 and you will get the point. We have the intersections. Intersection. Which is, so x is 2 minus 6, that's 2 minus 6. Y is negative 8. C is 5 minus 2, which is, so I just use one more step. So negative 4, negative 8, 3. Okay. Any questions so far? Yes.
Is it positive 8 or it's because y is the negative value? It's negative 8.
Is it positive? Very good question. So I believe you are correct. So negative 4 times negative 2 plus 8. Very good. Very good. So you need to be definitely careful. Okay, so sometimes when you are looking and talking about something else, and you may mess up with this all. Right. Now so far so good. Now everything is good, right? Okay, very good. Example. So the next example is a little bit involved, but I would like to mention that this example is very important, and I believe the practice exam is available already. So there's a question in the practice exam that's even more complicated, and that's also about the lines and planes. Okay, just it's not. Let's look at this one. Find symmetric equations of the line L the L as L is the intersection of two planes, so as the intersection of the following two planes. So two planes intersect a line, right? But we want to get the symmetric equation. So the plane here is x plus y plus equal to 1. And another plane is x minus 2y plus 3z. So basically, what we need is actually for the equation of the line, we need what? We need two things. One, any point on the line will be good, right? The second feature is that we need the direction along the line, right? So firstly, let's get that point. So since the line is the intersection of these two planes, so basically you just find whatever XYZ pair tuple, excuse me, you just find whatever XYZ tuple that satisfy these two equations at the same time. That will be a valid point. Okay? You find a point on L, cap L, noting that its coordinates XYZ should satisfy both equations. Of planes. So yeah, here I'm just going to copy this system. But now, if you think about it, actually the intersection is a line, so there is degree 1 of freedom. So what I'm saying here is that we have 3 variables and 2 equations, right? So here, well, we can specify, let's specify a value of z. So if we fix that as a constant, then you're actually fixing 1 point on the line that you have, right? So let's say setting, let's say z equal to 0. So that will be easier. So if you make z equal to 0, then you have a simpler system of equations. That is now x plus y equals to 1. And x minus 2y equals to 1. Okay? So now z is gone, so we have a little bit less of a degree of freedom. So we have 2 equations and 2 variables. And if you do either by a rule of elimination or rule of substitution, you can solve that x must be 1, y must be 0 here. That tells you 1, 0, 0 is 1 point on the line, FL. Okay. Any questions so far? So the line, so we have now 1 point, right? And then we need a direction. Okay. So we just need to realize that this line is contained in both of the planes. So the dual vector of each of the plane is going to be perpendicular to the line that you have. Okay. So let me write that down. So the normal vectors of the planes are, so basically just look at the equation of the planes. So for the first plane, the normal vector is 1, 1, 1. This is the coefficients in front of x, y, z. We call it n1. And then we say n2 is the vector that's 1, -2, 3. Right? It's reading off the constants. But we know, let me finish this sentence. Since cap L lies on both planes, L is perpendicular to both normal vectors. And hence, L is parallel to the cross product of L N1 and N2. Okay. So basically here, we want to get the symmetric equation. So we want to get 1 point. So this is a figure that I have sketched on the right hand side of the problem. Basically, you have the two red things, and then there's the intersection of this purple lines, right? And then you want a symmetric equation. So basically, you just need a point and direction, okay? So then you will be able to write x minus x zero over a equals to y minus y zero over b equals to b minus c zero over c. Right? And then how do we calculate the direction of the line? Okay, so if we look at this, on this side, the red vector n1 is the lower vector is perpendicular to the thing on top. Okay, so the circle. But then if we turn to the other, so that tells you, okay, this n1 direction must be perpendicular to the purple line right there, that's the intersection. Okay, and at the same time, if you look at the plane at the bottom, the lower vector n2 is pointing outwards. Okay, it's also perpendicular to that purple line. Okay, so essentially, you know that the purple direction is perpendicular to both of the normal vectors of the planes. So here, what I circled is the normal vectors that I somehow moved to that line, and then okay, so definitely, so you have the line direction in purple to be perpendicular to these two normal vectors. So you just want to do a cross. That's exactly what we have done from last time. So sometimes this kind of illustration definitely will help you. But I hope you have the time to sink into the process we have done from last class. Actually, this is a very, very important type of question. Okay, so playing with the definition of the line of planes and what are critical. And of course, this is not the hardest kind of problem. So in particular, I'm referencing to one of the practice exam questions that is a little bit more involved, but actually you guys now know everything that you need to know to solve it. Okay. So basically, we found out the cross, and then we just put them down as the bottom of the symmetric equation, and that's it. Right. Any questions so far? Okay, if that's good, then let me so. Right. The next topic is a remark, a quick remark. So we just in this example, what have we done? We have two planes, and then we want to write down the equation of a line, right? So if you think about the equation, exactly, if you think about the symmetric equation, so remark any line of the form x minus x zero over a equals to y minus y zero over b equals to z minus z zero over c. You can think about it as intersection of two separate planes. This can be regarded as the line of intersection of planes. So now, if you think about it, okay, we have three parts, right? We have three linear parts. They have to equal to each other. So you just choose two out of the three, and then you will be able to find three planes, right? So and you just any two. Let us say this part is a plane. This part is a plane. Okay. So now our line here is the intersection of these two planes. So then write that down. X minus x zero over a equals to y minus y zero over b, and y minus y zero over b equals to z minus b over c. And you see here, the common expression is the y minus y0 over b, this part, right? And basically, for the three expressions that are equal for the linear, for the symmetric line equation, you can just pick whatever expression in common, right? So that will give you, let's say, if this in common, then the x part equals to z part is a plane, a y part equals to z part is another plane, right? So, anyways. Right. Final remark. So now, for two planes, this is a remark, and this is a fact that may be useful when you are trying to solve a problem involving planes. Okay? For two planes, if the normal vectors if the two normal vectors are parallel, then the two planes are parallel. So basically, when two normal vectors are parallel, that just means okay, the normal vector is essentially the same direction. Okay? And it tells you basically you have a line, the normal vector direction, and then one of the planes perpendicular to this ray. There's another plane that's also perpendicular to this ray. Okay? So those planes have to be parallel. Okay? And vice versa. So basically, if you have two parallel planes, and then the normal vector is not parallel, obviously. That's the last one. And that finishes our really long section on the lines and planes.